The second half of this unit deals primarily with periodic trends. How do the properties of the submicroscopic level, including electrons layered in different energy levels, protons in the nucleus, the attraction of those two things together, and the repulsion of electrons with each other, how do those influence the trends that we see on the periodic table? Coulomb's law is something that we're going to keep coming back to in this second chapter, chapter 7 in unit 1. The magnitude of the electrostatic force of attraction or repulsion between two charges is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. Two things that have opposite charges will attract to each other. The force of that attraction is equal to some constant times the product of the magnitude of the charges. So if you have bigger charges, it's going to make the numerator of Coulomb's law bigger, which makes the force, therefore, bigger. However, the distance, or the radius simply means the radius from this to this, or this to this, the distance between them squared, has an inverse relationship with the force of electric attraction. So if you separate two things that are attracted to each other by a greater distance, it will make the force of attraction much, much, much smaller. This also applies for things that have the same charge. If the same charge is put next to, like a negative charge and a negative charge are placed next to each other, they'll repel by this force as well. Coulomb's law can be used in any justification of the periodic trends that we're going to quickly review. Anytime charges are changing or the distance between those charges are changing, that's when you can really refer to Coulomb's law in a good justification of the periodic trends. We're going to be talking about protons and electrons. Those two things attract to each other. We're also going to talk about just electrons and how they repel each other if they're close together in an atom. Quick backdrop for the periodic table. Two scientists simultaneously around the mid-1800s came up with the current organization of the periodic table. The first way in which they were placed together was based on atomic weights, and then Henry Moseley came by, fixed our periodic table, and put the elements in order based on their atomic number, which corresponds to the number of protons. One thing that I want to quickly review is effective nuclear charge. That's a big buzzword that's going to be coming up at various points throughout our discussion of periodic trends. The outer shell, which means the highest principal quantum number electrons, have two things going on. The first of which is, well, those electrons are attracted to the nucleus. So the nucleus is actually pulling on those electrons. There's also another force that's acting on outer shell electrons that are in the outermost energy level. If there are any electrons in between the outermost electron and the nucleus, the electron that's in between, or a core electron, pushes outward on the outermost electrons. This effect is called shielding. Shielding is not necessarily a force field put in place by the inner core electrons, but really it's more so just a force that's being applied by the inner shell electrons pushing the outer electrons out. For any outer shell electron in an atom, we can calculate or approximate the effective nuclear charge. This is a general equation. It really doesn't follow every element. Every element does not follow this rule. But a general approximation of the effective nuclear charge that is being exerted on the outer shell electrons is the Z, or the atomic number. So in the case of sodium, 11 protons, right? Minus the number of shielding electrons. So in sodium, it has 10 shielding electrons. I'm just using these positive and negative symbols to show you I'm talking about protons and electrons. So the overall effective nuclear charge that the outer shell electron feels, and that's an arbitrary term, but feels in an atom of sodium is actually only a positive one. Now, this is only an approximation. You can actually look up something called Slater's rules governing effective nuclear charge and how shielding affects effective nuclear charge when we get further down in the periodic table. But for the time being, we're going to be referring to these concepts when we describe periodic trends. The atomic radius is defined as 1/2 the distance between two atoms that are bound by some kind of chemical bond. And the reason why we cut this distance in half is it's the best experimental way for us to approximate the distance between the nucleus and the outer shell of an atom of that element. You can also use this technique for things that are stacked together as crystal lattices, such as ions and metallic substances. But really, the atomic radius is simply just how big the atom is. Here are our two trends in terms of atomic radius. Atoms tend to get larger from top to bottom down a group. So if I look at my alkali metals, rubidium is the biggest, or it has the largest distance to its outer shell. The principal quantum number is increasing. It's increasing the number of orbitals. It's also increasing the radius of those orbitals. So there's two ways to look at this. Rubidium has 5 energy levels of electrons. So it has 4 energy levels of electrons that are shielding the outermost shell. It's repelling it and pushing it further out. You can also just relate this in terms of distance, right? The 5th energy level is 1, 2, 3, 4, 5 shells out, which therefore makes it a larger atomic radius. Now, the other thing that we notice is if we stay in the second period, so if we go from lithium all the way down to fluorine, as we go from left to right, the atoms actually get smaller. There's one reason why this is happening. The effective nuclear charge is getting bigger as we go across the periodic table. Well, you'll tell me we're adding extra electrons, so shouldn't they be repelling each other? Well, not necessarily. The extra electrons that we're adding are being added to the valence shell. We're not adding any inner core electrons that are increasing shielding. So therefore, the effective nuclear charge is going from 1 to 2 all the way down to 7 for fluorine, if we use that approximate equation. So the number of protons is getting bigger and bigger and bigger and bigger and bigger. Bigger protons, Coulomb's law says that those protons are going to attract to those electrons with more electrostatic force. Let's see if we can quickly look at the periodic table and start to make some approximations about relative atomic size. Before we start to put these elements in order, I go through the priority of what affects atomic radius the most. Number of energy levels has a much bigger impact on atomic radius, and there's really two reasons for that. The first reason is because with more energy levels, you also have more inner energy levels that are shielding the outer electrons and pushing them out further. That's reason number one. And reason number two is if you go back to Coulomb's law, the distance squared, that's the key, is the distance squared has an inverse relationship with the force of attraction. So if we increase the distance, it's having a bigger mathematical impact on things. Then, if two elements share the same number of energy levels, then we're going to use the number of protons as a tiebreaker. More protons are going to make the atom shrink and constrict. I'm going to give you a moment to try to put these 4 elements in order based on their increasing size, and then we're going to justify our answer. I draw these pictures to help me prioritize. Well, first, the number of energy levels. Well, why did I draw 3 for these 2 elements? They're in period 3. Period 3 elements have 3 energy levels of electrons. These two elements were in period 4, so I drew 4 energy levels, and that makes these two elements obviously bigger than these two. The tiebreaker is, well, between these two elements, sulfur has 16 protons while phosphorus has 15. So sulfur is going to feel more effective nuclear charge than phosphorus. And the same reasoning holds true over here. Selenium is going to be a little bit tinier than arsenic because selenium has more effective nuclear charge in its nucleus. When you're justifying these trends, you should refer to Coulomb's law, and you should say increased number of protons increases the force of attraction according to Coulomb's law, therefore it makes the atom or the atomic radius smaller. You can also refer to distance, right? Distance is also in Coulomb's law. Greater distance between the outer shell electrons, less attraction towards the nucleus, larger radius. Go ahead and take a moment and see if you can put these elements in order of increasing atomic radius. Starting with beryllium, beryllium would be the smallest, followed by magnesium, and then we would have sodium. Sodium has an extra energy level of electrons, extra shielding, pushing on those outer shell electrons. Beryllium has the least amount of energy levels, and it also has the most protons in that period. We'll move on in our next video to the sizes of ions and what controls the formation of ions as periodic trends.